Great. Thanks for having me here. It's nice to see the young people here. I know. Oh, I have.
Whatever. Would you like to for this?
This one. Oh, it's okay. It's good to see the young people here. I know the old people were out drinking and singing last night. So I'm told I wasn't there, but I'm told that they were out doing that. So they may be resting at the moment, but the young people here, I'm glad to see you. And so I wonder what to do in 1 hour, or actually 50 minutes that I have to talk, because in this kind of a time, you can't tell people how to do something that will take them most of the rest of their lives to do, but I want to try and give you an attitude or a direction or maybe a way to learn how to proceed when you're going to analyze data. And it's something that worked for me, and it's something that has worked for others who have worked with me, especially Shang Liu, who was there. I had Shang come in and start to work on ozone profiling with me. And the wisest thing that Shang ever did was to not listen to me tell him how to do it, but to figure out how to do it himself. And the result has been absolutely brilliant. So the background for this first slide is, in fact, a movie of tropospheric ozone from Shang. And so for my first slide, I don't know how well do you know this animal in Korea, but you know it. It's an animal that comes along when you don't want it to be there and makes a bad smell. But sometimes that's our job, because we say in American, we say our job is to be the skunk at the garden party. So you're out, you're having a good time, and this thing comes along and spoils the party. And if you're doing atmospheric science, in fact, it comes along because our job is to tell us how to be rigorous scientists where other people have been maybe not doing such a great job but enjoying their life doing not such a great job. So I hope the humor works. But in the West, in the old days, science was done in Latin. And now mostly people do not learn to do Latin. There are a few remaining places at Harvard. People still learn a bit of Latin sometimes. But this is one of my heroes, and it's one of the heroes of astronomy, in fact. And this is William of Ockham, this guy here. He is an English philosopher of many, many years ago. And he wrote this thing called Occam's razor. And a razor is not something you shave with. A razor is a way to proceed in doing what it is you're doing. And he wrote it in Latin, and we don't need to read the Latin, but we need to know that Occam's razor says, as astronomers love, that you should avoid needless complexity when you're about your business, and our business may be analyzing atmospheric data. And in particular, don't make your algorithm more complicated than it needs to be. You should make your algorithm as complicated as it needs to be, but no more. And so for our German colleagues in particular, and there's one over there, you should avoid Verschlimmbesserungen. So avoid no Verschlimmbesserung. So Verschlimmbesserung is my favorite German word, and what it means is an improvement that makes things worse. And we see those very often in life and in atmospheric science in particular, but we see them in American politics, of course, too. So we don't add things to our analysis that make it more difficult but don't make the answers better. So we'll go into that more. Now let's see. This doesn't work so well. Okay. On the sideboard, you can see that you have here in the background these things that don't really show up. The middle doesn't show up here very well. But on the side, you see that you have the Ten Commandments that Moses brought down from God on the mountain. And so I use that as the background for the rules. And I'm not God, so I only have 5 commandments, and we'll go over them in a moment. So commandment number 1 is you don't define your algorithm in advance. And why am I bothering to do this? I'm bothering to do this because we started a long time ago with Schemaki, and then we had GOM, and we had OMI, and we had GOM2, and we had OMPS. And whenever people decided what the algorithm was going to be before they actually saw the data, they always got it wrong. So in the case of GOM in particular, and in instruments following on to GOM, we heard that, we're going to do these wonderful ozone measurements. GOM was the Global Ozone Monitoring Experiment. And starting in 1989, we said, we're going to do this, and we're going to measure ozone, and we're going to use this wonderful modern European method of measuring ozone, or in analyzing ozone, rather than this terrible old-fashioned American method of measuring ozone that the TOMS people were doing. And so instead of doing the TOMS method of analyzing ozone, we're going to use the DOAS method of analyzing ozone. Well, it turns out, and we'll see a bit more later as well, that the DOAS method of analyzing ozone was a Verschlimmbesserung. It was an improvement that made things worse. So, but the method, the lesson to take away from that is that you shouldn't decide ahead of time what your algorithm's going to be. You're physicists, we hope, scientists. You're not going to be mechanics that fix the cars, but you're going to be the people that figure out how the cars work. So you will do the physics, and you will test things on the data when the data come in. So you won't decide your algorithm in advance, ideally. It's a little tough because you're working on gems and working on tempo, etc. But when the data come in, we're going to have to look at them and see what works the best. And in fact, we'll have to test all of the steps in the algorithm for the utility and the applicability to getting the answers out. And we're going to hopefully let the physics guide us. And it seems obvious when I tell it to you, but when we talk about it in the context of satellite experiments in the past, it hasn't always been the case. In the U.S., a black box means a device that does something and you never see the insides of it. So we'll say no black boxes to an American means we don't have something that we don't know what it does, but we know what comes in and we know what comes out. So we say no black boxes. If you're going to be a person who analyzes data, you must have all access to all aspects of the data, including all of the source code. And you saw me yesterday nag about, will we be able to see the source code for the 0 to 1 processor? There are times, like with OMI, where the scientists couldn't see the way that you went from level 0 data, so the uncalibrated radiances, to level 1B data, the calibrated radiance with the geolocation data on there. They weren't allowed to see it because that software belonged to a company. That's not going to be the case in GEMS. It's not going to be the case in tempo. But in any case, if you're doing the data, you have to see and know everything that's in there, and you have to be able to modify it as necessary, and you should test all of the assumptions that go into the processing of the data. Again, more later. But when you do that, if you're analyzing spectra, I call it Occam's taser. Occam's razor was his great insight that you have to avoid needless complexity. The taser is the thing that the police shoot at you to knock you out if you're misbehaving. The Occam's taser here to me is that if you're analyzing spectra and if you didn't do it yourself, it hasn't been done. If you're taking something that someone else has given you and saying this is the way forward, you must be very, very suspicious. You have to do it yourself, and you have to do it all the way, I said, down to bedrock, which means to the lowest physical principles and the lowest principles of the spectroscopy, and you have to understand and, if necessary, publish all the reasons why you're doing that. And when I get through with this slide, I could stop, and then if you've digested all of that, you'll be well on your way to analyzing data. But I'm not going to stop there until they tell me I'm out of time. The next rule is that reference data should be reference data spectra and other reference data that you need to analyze your spectra must be peer-reviewed, published, and publicly available. I call it P-cubed. And it seems so obvious. And you're saying, well, why is he telling us that? I mean, it's obvious that you should do it. But in fact, in the world of atmospheric measurements, that's not always the case. You will find people that will take, and the worst offender is the spectrum of the oxygen collisional complex, O2, O2, or we call it O4 sometimes. People will say, well, it works a little better if I shift the wavelengths a bit over here. Or if I skew it a bit this way, I get better results. And you just can't do that. You can't do rigorous science if you mess around with your reference data. So no unexplained shifts in the cross-sections, for example. Sounds obvious to us. Our colleagues in Europe have done exactly that and have published data that rely on not using laboratory data that were actually measured and published. And then the final thing is the NAG. And coming to Korea is really so nice for me because the students are so smart and they're so hardworking and they know their physics. And so I can say to them and to you that the physics has to be done with the full rigor. So when you're looking at Raman scattering, you should understand the physics of the Raman scattering, which means the quantum mechanics underlying it. You should understand what the radiator transfer things going on are, and you should understand enough of scattering theory and spectroscopy to do things in great bloody detail. And if you do that, we will beat the world in how we measure atmospheric things. Okay? So that was so on the western side we have the Ten Commandments, but we're in Asia now, so this is Confucius, right? So Confucius is telling us the same thing, that the wisdom of Confucius says that we have to do things basically correctly, and then we'll be great. Okay, so here's an example of some spectra that we used when we actually did, in this case, the first global measurements of formaldehyde from space. It was a nice piece of work. It was this is the proxy for volatile organic compounds from space. And the point of the slide really is down here at the bottom, which is not just that we can measure these things, but that when we successfully analyze data, we start by looking at spectra as individuals. And that's been my approach in fitting of spectra. So it's not that you will take some body of software, some program of software that someone has given you, and you'll maybe test a day's worth of data with a selection of reference data and a range of wavelengths that you fit and see what you get. But you should go to individual spectra and look at them in great, great bloody detail. And that's how we made fitting of formaldehyde work when our colleagues, frankly, in Europe were saying that GOM could not measure formaldehyde. We did the algorithm physics and measured formaldehyde. So successful fitting is done by looking at spectra individually and addressing every aspect of the algorithm. And when I say the algorithm, I want to go back to the physics, so algorithm physics, and looking at the various things that go into the physics, not just the range of the wavelengths, but the things underlying, like Raman scattering, closure terms, underlying spectroscopy, etc. So when you are successfully analyzing data, you will look at spectra and you will figure out what's going on in them, and you will not pay attention very much, except for some general guidance, to what the old people, like myself and others, have told you you must do in order to analyze them. So let's look for a few minutes at what the kinds of things we're measuring are. Okay, so this is a list of past spectrometers. And I'm starting here with GOM, and the green things should be the instruments that measure in the nadir. So we actually started Skiamaki in 1985 when Dieter Perner of the Max Planck said that would be a good idea to do based on his ground-based measurements. And the first thing to fly was our GOM1 instrument, followed by the GOM2 instruments, and then Skia gave us 10 years of great data. And then we have these wonderful things that have flown and the wonderful things that are going to fly, like GEMS, which we're talking about today, that will make nadir measurements and measure this wonderful array of data products. And I tend to emphasize the gases, but certainly the aerosols and the clouds are equally as important. So that's the background, and what we're going to measure looks like the following. So here are some GOM1 data, and GOM1 data are wonderful, although they are flawed. So here is an irradiance measured with GOM1. Irradiance, so that means we're looking at the solar spectrum. And this is a funny thing that cancels out. It's in the calibration of the intensities that cancels out in the radiance and the irradiance. But this is a spectrum, this is a solar spectrum in photons per second, per square centimeter, per nanometer. Here is a radiant spectrum, so now looking at the Earth, photons per second, per square centimeter, per nanometer, per steradian. And then if I take the ratio of them and take the steradian out, that's why this pi is there, and this mu zero is the secant of the solar zenith angle, then I get this albedo or reflectant spectrum. This happens to be a very cloudy looking spectrum, so it's bright like that. And these are the kinds of things that then we're going to measure. So let's look at in a little more detail. So here are some, again, GOM spectra. Now we have GOM and we have OMI and we have OPS and we have GOM2 and etc. And I keep showing GOM1 spectra. And the reason that I keep doing that is GOM1 made the nicest spectra. All, the other instruments following that have been wonderful as well, and they've done wonderful, wonderful things, but our first child still has been our prettiest one. And that is, and of course we love all of our children equally, but GOM1 has given us the best spectra. So here are the extremes of what one sees in an Earth spectrum, and I'm going to go through this quickly because I'm going to go on to more in the next slide. But in a bright spectrum, so a cloudy spectrum here that is bright, we see all of this stuff that we fit, and we see the oxygen bands, and we see water, etc. And a cloudy spectrum is bright, so it's one would be a white radiator. So cloudy spectra are almost white, and they're very bright, and a fully cloud-free and ocean-looking spectrum is dark, and it's blue. So here's the spectrum of the ocean, and its albedo down here in the infrared is down to less than 2%. If I go out to Skiamaki wavelengths where we measure CO2 on the ocean, it can be less than 0.1%, which is why when we say, well, we can't measure CO2 over the ocean so well, it's because it's really, really dark there. And then the growth of the spectrum as we go to shorter wavelengths is because of the Rayleigh scattering, and the stuff poking up the wrong way is because 4% of the Rayleigh scattering is inelastic. It's Raman scattering, and in the atmosphere we call that the ring effect. So the solar spectrum, when it's scattered, gets broadened out into the Raman spectrum of air, right? 80% nitrogen, 20% oxygen, and when you divide one by the other, they don't cancel out, and you get the stuff sticking up there. So in a bit more detail, okay, here is the spectrum of the Earth. I live in a place where we have astronomers, and astronomers are looking for, trying to find Earth-like planets that might support life somewhere out there around other solar systems. And they wonder, gee, what might the spectrum of an Earth-like planet look like? And we keep telling them, well, maybe the best thing to do is to look at the spectrum of the Earth and see what that looks like, and that may guide you in what an Earth-like planet might look like. And they're mildly interested, but not very much. But here is what an Earth-like planet looks like. So here is, you saw before, a cloudy, bright spectrum. One would be a perfect diffuse reflector. The ocean down here, so it's dark, and it's growing in the blue because of Rayleigh scattering. Oh, and the desert in here looks like this. So you see growing toward the visible in the infrared, because deserts can be bright there. And then if you look at vegetation, you see this. And vegetation is darkish until you hit this vegetation red edge, and it comes up. And looking in here and maybe looking at fluorescence in there is a way to tell you that you're looking at aspects of primary productivity of carbon. And if you look very closely, it's a little hard to see, but you'll see a minimum, or you see a maximum right in here in radiance, which is a minimum absorption, and that is the minimum of the absorption of chlorophyll. So if you were to take a linear combination of these spectra, you'd have the spectrum of a terrestrial planet. Okay, I better move on here so that next guy can talk. We can go after further wavelengths, and here's one example from Skiamaki, for example, and so GOM stopped in here. Skiamaki keeps on going continuously to 1.7 microns or 1700 nanometers, and then has further two channels in the infrared here and here. And then we're going to be looking at absorptions and trying to measure gases in these spectra. So I'm going to emphasize, well, in the first place, the GOM stuff. And here is an oldish slide that looks at GOM and says, well, in a typical geometry, so average viewing geometry, average amounts of stuff, what do we see in terms of backscatter from GOM? And I'm looking at the logarithm of the absorption optical depth. And this is a little older slide, so this dotted line should be a bit lower. But this says, what's the best that we can do? The best that we can do is on a good day, about 2 times 10 to the minus 4 of the radiance, or signal to noise, of about 5,000 in measuring these things from GOM in this case, or Skiamaki, or OMI, although OMI is not quite that good. And here are what the optical depths of the things that we're measuring are like. So we're doing quite nicely. Here's a bit more specific case for a geo instrument that looks like GEMS or tempo. So GEMS is going out to here, and tempo is going to then continue over in here. But in typical measurement geometry, we'll see optical depths of these gases that look like this, and we will, if we have done our work well, which I know you will, measure down to this kind of a level, and see logarithmically these kinds of things sticking up, and do a very nice job of measuring what's in there. We don't have to worry about this. This is a way of selling future instruments that we were actually successful in doing, since we sold tempo. Okay, so let's look at the. We're going to look at the physics a bit more, and I'm dealing with Microsoft, so things are moving around on me a little bit. So I keep moving this arrow over to here to about 3.5 microns. So this should be over here, and this is to show you. This is a slide from my old friend and colleague Judy Lean at the Naval Research Laboratory, who is probably sitting at home because she's on furlough at the moment because the government is closed. But it shows you what the solar spectrum looks like and what it looks like at the Earth. And even more importantly, if you can read it, it tells you what the variation is over the solar cycle. That came into the discussion, I believe it was yesterday, when people were saying, well, how, it varies a lot with solar cycle. Well, and it turns out that at, say, 300 nanometers, 1, 2, 3 here, it's not so bad. It's only when we get to shorter wavelengths than that the variation changes. If this arrow were over here where it should be, it would tell you where you measure things by solar backscatter radiation, which is to these shorter wavelengths, and where you measure things by emission in the atmosphere, which is at these longer wavelengths. So more on that here in a second. Okay, here. So if we are up and we're looking at the planet, and the planet is filling most of our field of view, and the sun is a little thing up there, then we are seeing emission down here. We're seeing backscatter radiation up here. And we will do our measurements in a way that takes advantage of the fact that we have backscatter here and emission here. And if we're doing CO measurements, for example, like we would like to do with Kronos, or like David has done with Moppet, we would do backscattered measurements in here of the overtone band of CO that are sensitive fairly evenly all the way down to the surface, and at the same time we would do measurements of the emission of CO in here that are sensitive to the middle of the troposphere and not so much to the surface, and then we could combine those and know a lot about how CO is distributed in altitude in the atmosphere. So a little more here about the physics. So I'm going to look at the solar spectrum, and the solar spectrum it looks so much nicer on the sides, doesn't it? Yeah. But the sun is very complicated. And so it has all of these structures in there. And most of the time we're measuring in here and in here where it's very, very complicated. And it's complicated, and what it's doing is, so you have at the bottom of the photosphere of the sun, you have more or less a black body with this kind of envelope and an emissivity of maybe about 80% that is illuminating the photosphere of the sun, and then all the stuff that's absorbing, because there are molecules in the atoms that haven't been dissociated because they're not so hot, are in that narrow photosphere, and they have an envelope in their absorption spectrum that looks like the bottom of this, and in between we have this spectrum. And it's very complicated. And so I say that even though with a lot of work you can figure out what's going on in the sun, and our colleagues do that, and they know what every tiny little thing means. In terms of atmospheric measurements, there are no lines in the solar spectrum. There's a structure. There's an overall structure. So you'll hear people say, well, we're going to look at a Fraunhofer line. And if you're doing atmospheric spectrum, that's not true. You're never looking at a Fraunhofer line. You're looking at the resolution of the instruments that we're talking about at complicated structures. And that's important, as we'll get into in a minute. The quasi-continuous nature of the spectrum, the fact that it's complicated, means that you're never looking at lines. So sometimes you'll see people say they're doing cloud measurements or doing ring effect measurements, and they're looking at filling in of Fraunhofer lines. If you look at the physics of that in a bit more detail, you're never looking at the filling in of Fraunhofer lines, and you're wasting your time if you try and do it. It's an incorrect approach. Filling in of Fraunhofer lines to do clouds, Raman scattering, anything else, is the incorrect physical approach. They're highly instrument dependent, they're time dependent, they're wavelength dependent, they're instrument degradation independent, and calculating what it is the sun is actually doing, which is not more complicated, is a much better approach. And this bottom part is from my course, and then it's basically, remember our friend the stinky animal is reminding us that when we're doing all of this stuff, we always do our wavelengths in vacuum. And it shouldn't be, it's not rocket science to say that, except that many times it's not the case. People who should be doing this are not doing it. Okay, so let me talk a few more minutes about the solar spectrum, because it's really, really important, because that's our light bulb when we're measuring atmospheric spectra. So the high resolution irradiance is critical. We use it for a bunch of things. We use it for our wavelength calibration. So these instruments like GEMS and like Tempo and GOM, OMI, etc., they do some wavelength calibration in the laboratory before they're launched. That's a convenient place to start. And even then, it's not really necessary. We could do without it. the best wavelength calibration comes from the solar spectrum, which we know, by the way, from careful analysis, here where we're measuring in tempo and gems, we know to 2 parts in 10 to the 7th in absolute vacuum wavelength accuracy where they are. And we can use that to do our wavelength calibration. And here I give it for GOM, but I could give it for any other instrument. So for GOM radiances and irradiances, we can determine the wavelength scale of our radiances and irradiances to this kind of an absolute vacuum wavelength accuracy, which is much better than 1/100th of a resolution element, just by doing a cross correlation with the solar reference spectrum. We use it for other things, like when we have to do this ring effect, which is, remember, it's the inelastic part of Rayleigh scattering, so it's the Raman scattering. We can use the solar spectrum to determine that quite accurately. We can correct for not Nyquist sampling the spectrum, so spectrum undersampling, and we can actually, when we get lazy and come in on weekends, we can do some science with it. We should have had by now a space-based better determination of the solar spectrum. We didn't do it. Older versions of the slides have suggested that Europeans do it or the Canadians do it or whatever, and so maybe there'll be an Asian instrument that will do it properly in the future. We'll see. So here now I'm looking at the wavelength calibration, and I'm also going to talk about the slit function because that was discussed yesterday a bit. My colleagues at the Center for Astrophysics years ago, Tonry and Davis and computer programmers who worked with them, developed a way of measuring redshifts of faint galaxies. So they were doing cosmology, and they would take spectra of galaxies far, far away, and they would have reference galaxies nearby, and they would tell how the galaxies far away were redshifted by taking their spectra and correlating them with nearby ones. And we adopted this software in the first place for GOM, and it was Christoph Kaspar, Visa, and myself did this to see what the wavelength calibration of GOM was like. So GOM was our galaxy far, far away, and the solar reference spectrum was our nearby reference galaxy. And we first developed this, and then we made it into standalone software, which now works on GOM, and it's been adopted in Skiamaki and OMI and OPS, and we'll use it in Tempo, and I hope we use it in GEMS. And it's very, very accurate, and it not only tells you the wavelength calibration, but also if you have a model for the shape of the slit function that can be parameterized with 1 or 2 adjustable parameters, it will tell you in orbit what your slit function is and how it has changed from what the slit function was when you calibrated it in the laboratory before you launched it. Okay? So it's very accurate. It's normally much better than 100th of a detector pixel. The other nag point of this slide is that when we start doing these spectra, right, so we have spectra far, far away, and we're trying to get down to very, very precise fitting, we're going to have to fit them in a nonlinear fashion, where the nonlinear part is mostly the wavelength scale. Okay? So, fitting of atmospheric spectra is almost always intrinsically nonlinear. Sometimes, if you're lucky and you're doing ground-based measurements, linear fitting will work. Usually not. Linear methods are seldom appropriate and seldom useful except sometimes if you're doing ground-based measurements, and usually not then. Okay? So DOS fitting, for example, and you hear DOS a lot. DOS fitting includes steps to try to linearize the Beer-Lambert absorption, but in satellite measurements, and mostly in ground-based measurements, you then go ahead and do a nonlinear fit anyway. So DOS is, that's why I say you don't want Verschlimmbesserung, in which you don't want improvements that makes things worse, like trying to linearize a spectrum that's not linear. Okay? Now here's an example of that. So I'm looking at the ring effect. How am I doing in time here?
10 minutes. We started 5 minutes late.
10 minutes? Okay, I'm fine then. Okay, so here's an example when I'm going, now I'm in the NO2 fitting region for GOM. And this paper I did with Rob Spur in the old days. And so here's a piece of the solar reference spectrum, and it looks very complicated. And then if I take this spectrum and I convolve it with the GOM slit function, it looks like this. The Omi slit function, Skiamaki slit function, GEMS tempo would look very similar. So I've done that. So this is still a solar spectrum. But then now if I look at that and say, well, gee, what if I'm measuring the Raman scattered part of the backscattered spectrum? What does that look like? And that looks like this. So you can see it's a more slowly varying, gentler part of this spectrum. And so if I'm fitting spectra directly, which is what I like to do, and what I like to sometimes call BOS fitting for basic optical absorption spectroscopy, which is also just taking a spectrum and fitting it, I would use that. But if I'm doing DOS, which says that I've taken my radiance and divided by the irradiance, taken the logarithm met, high-pass filtered that, I get something like this for my ring spectrum, where all of the structure in there is not from the Raman scattered light at all. All of the structure that's visible in there is from the fact that you've divided your radiance by the irradiance. And also, now that I'm trying to fit a spectrum, instead of having a radiance and an irradiance that I have to match up, so I have two hands that I have to do this with. If I'm doing DOS, I need a third hand to do 3 high-resolution things to match up. Okay? I have some details which I'll skip here on more details of the ring spectrum. This is our friend William of Ockham, and this is the fact that if you're doing Raman scattering correctly, you need to take into account the triplet structure of the oxygen, which mostly we don't. If you're using a ground-based determination of the ring effect, you need to do the algebra of the fact that you have inelastic scattering properly here. Again, I won't go into the details, but most of the time the algebra is not done correctly. But in fact, if you do it all correctly, then you see in this example where I've fitted a piece of GOM spectrum for BRO, and here is the fitted amount, and here is the fitted amount plus the fitting residuals. You see that I can fit down to very, very fine fraction of the radiance or very high signal to noise, even when the ring effect contribution here is an order of magnitude larger. And I think while I'm here, I should say to the students among you, when I say you shouldn't listen to the old guys, that includes me. Whenever you're developing fitting stuff, you need to do it yourselves. So not only don't listen to the old guys everywhere else, don't listen to me. Try it yourself. If you haven't done it yourself, remember rule number 2 is if you haven't done it yourself, you're being a mechanic and not a scientist. Here's another nag about the filling in of the Fraunhofer lines. If you treat them as filling in of lines, you're not doing the physics correctly. And you don't need to treat them that way either. Gohm, Skiamaki, Ome, Amps, Tempo, GEMS, all undersample the spectra. Tempo and GEMS are better than previous instruments. So it's less of an issue now with us than it was the instruments in the past. But when we do have undersampling, we do have the ability to use that solar reference spectrum to calculate an undersampling correction to the spectrum. I won't dwell on it. We don't need it so much, and we have it available anyway. We have it in a way we developed at the Smithsonian that's used for all these instruments. KNMI has also developed an alternate for it that works quite well. So now we're going to fit spectra, and I'm going to speed up a little bit. We're measuring all of these kinds of things, and our aims are to measure all of these gases and then to do the science with them and to look at the pollution from them. And so we have to do all this complicated stuff. So how hard is it? So it's mostly hard in about this scale. So the toughest thing has been formaldehyde. And we could argue all day about the details of this slide and what's harder than the others. But roughly it's a sliding scale from being hardest is formaldehyde and the easiest is NO2. But doing it properly requires precise and dynamic wavelength calibration that I've mentioned, correction for undersampling and the reference spectra that I've mentioned, and we can debate about those in a minute, but again, you must be very careful not to use improper and not well determined reference spectra. And then we do the fitting. And in our cases, the best fitting is from direct fitting of the radiances, not the logarithms of the radiances divided by the irradiances, high-pass filters and all of that. And then for ozone and SO2, we will do maybe a further optimal estimation kinds of fit. Okay? So we do, for most things, we do a nonlinear least squares fitting. We have a simple ring effect formulation because we know what the physics is and we don't have to talk about this filling in, which distorts our spectra. We do wavelength calibration. We do the ring effect quantum mechanically correctly, spectral undersampling correctly, and then we either divide by an air mass factor, or in the more modern world, we will pre-normalize our reference spectra to an appropriate air mass factor and get vertical columns directly. And then sometimes we'll have to take further steps, like especially NO2 needs further correction to do the troposphere and get the tropospheric residuals. To do all of this stuff, we need chemistry and transport modeling, and what we normally do at our places, work together with Daniel Jacobs' group with GeoSchem, and for radiated transfer modeling we use VLIDORT, which is Rob Spur's current program. So the vector version is here. It says in progress. This is null side. It's pretty well there, and this describes how you then relate chemical transport modeling and radiative transfer to the air mass factor to give you the correct vertical amounts. And here is an example for formaldehyde over Tennessee from the days when we were doing gold formaldehyde. And I think I got to finish up here. So I want to finish up by talking about the fitting. So we're doing nonlinear least squares fitting with lots and lots of optimization. We like to do fitting directly. I call it MOS fitting, which is basic optical absorption spectroscopy, or just spectroscopy. So we have, roughly speaking, a radiance is an irradiance here, and some albedo function, and some Beers-Lambert absorption, plus the ring effect, plus some closure terms, plus wavelength shifts that you have to include in a nonlinear fit. So if you manipulate these to try and linearize it, here you get a ring effect term, plus some higher terms, because taking the log doesn't quite get away with this stuff, right? And it's not a nonlinear fitting problem. I know our DOAS colleagues like to do a linear fit for the amounts, followed by a nonlinear term for the wavelengths, and a linear and a nonlinear, starting and ending with a linear fitting. And it's just not necessary. You do better doing nonlinear fitting from the beginning. So we like to do this, but we can do this, and in fact, in our algorithms, we have the options to do this, or this, or this, and this always works better. And if you're a young person doing algorithms, you should try it yourself and not believe me, and see what happens. And what you will find out, I'm guessing, will be that doing a direct fitting will give you about a factor of 2 or 3 in improvement, but it'll be a bit slower than doing a DOAS fit. So generally speaking, DOAS is less accurate, but it's faster. This is a NAG slide about spectroscopy, and the point here is, again, that you shouldn't take spectra from a guy in an alley who's selling spectra out of his raincoat. You should take spectra from proper database where they are peer-reviewed and published and publicly available. And if someone is messing around with the spectra, like putting arbitrary shifts and whatnot in them, those are not real analyses. Here's a good example of a real spectrum. In the present world, the ozone cross-section still needs some work. They're in pretty good shape. The thing that needs the most work is the oxygen collision complex. And that's the only thing that we have to use, that we can't use proper p-cubed reference spectra in order to do. Okay, this is one other fitting example, this was the first measurement of IO in the atmosphere, which we did with Skiamaki, and I think I'm getting right. Okay, I'm getting to the end. So I think I should stop there and here advertise who all of our colleagues that we work with on this stuff is, and listen to any questions that you have about an old surly guy telling you how to do your job.
Thank you, Andy. Very nice lecture. And any questions? You can ask any questions to Kelly. Okay, go on.
Thank you for your presentation.
And
I wonder, there is difference between the equation based on Lambert-Beers law and the equation taken by logarithm in fitting.
Taken by what was the
Logarithm, right?
log. When you take log of Beers law.
Oh yeah. Yes. There is a difference. I think we go back here, right?
Yeah, right.
Yeah.
Fitting first, is there difference between first equation and second equation in direct fitting?
Yes. When we started with GOM in the old days, the background was that so the European Space Agency was paying for this wonderful GOM instrument, and they were going to do modern ozone measurements. So they were going to use a modern European way of measuring ozone using this European GOAS method rather than the old-fashioned American way of doing a TOMS analysis. And so they used the modern European GOMS method, which is not just that, but which is this, the log, then high-pass filtered. Okay? The DOAS method was developed because of some guys in Germany that couldn't fit the baselines in their spectrum when they were doing some ground-based measurements. So they found that if they did this, they could fit their baselines. And since they were German professors, that was adopted into the GOM system, even though when we got GOM spectra and tested them, we found out that that didn't help. So yes, there is a difference, and physically, you were asking more, not this so much, you were asking, I think, about the difference between taking a radiance and taking the logarithm of a radiance. And the main difference there is that you're taking the log of a sum of terms, right? The logarithm of a sum of things is not a sum of logarithms, it's the logarithm of the sum plus some higher order terms. So we found out that if you don't take the log and just treat the ring effect as an addition to the spectrum and worry about your closure as an addition to the spectrum, you get better fitting residuals and more accurate results. So if there were no sums of terms, then there would be no difference. But there are sums, and the logarithm of a sum of things is more complicated than just the logarithm. Did that answer your question? Okay. Okay.
Now you said the formaldehyde fitting is the most difficult, and what do you think of which effect is the most important?
For formaldehyde. Well, for the formaldehyde fitting, it was important just because it was, to get global formaldehyde, the absorption was weak, and we had to get the Raman scattering correct down to a fairly low level, and we had to do all of the other algorithm physics right. So in fact, when we first got formaldehyde from GOM1 to fit globally, at the same time we got it to fit, one of our European colleagues was saying that GOM could not measure formaldehyde. So it was our biggest challenge at the time. And what is the challenge is mostly weak absorption. And in the face of weak absorption, you have to have better characterization of the things that interfere with the spectrum, which are not just other absorptions, but also Raman scattering, spectral undersampling, and those kinds of things. Now, it might be that with GEMS, it's not the most difficult thing. It might be that you come along and say, wait a minute, we have this list of molecules in GEMS, but I have another molecule that I can undo. Maybe GEMS can measure HONO, and maybe that will become the most difficult thing to measure.
Thanks. We better move on. So if you have questions, carry this around all day.
Mm-hmm.